Hello, I am Michael Nairn, and I'd like to welcome you to this webinar looking at polymer analysis on the MALDI-8030, with a focus on the analysis of pegylated vitamin E. In so many fields of interest, MALDI can assist your workflow. Here we will look into how MALDI can help you characterize your polymers. Polymers and polymeric materials are an incredibly diverse and useful range of materials, known for their ease of processing and their tunable physical and chemical properties. What is MALDI? MALDI is a powerful technique capable of characterizing a vast array of analytes, including polymers. Using a laser, our compound and the matrix are turned into an ion cloud, given a positive or negative charge. The following animation illustrates the basic process. The laser fires a pulse of ionizing radiation at the sample. The matrix and the sample absorb the laser energy. The sample and matrix are ionized. The containing voltage is released and the ions are repelled towards the detector. The ions are separated as they fly along the drift tube, with the smaller MZ ions reaching the detector first. We use this technique to measure the mass-to-charge ratio, m/z, of ions generated from our analytes. What do I need to perform MALDI? MALDI is a fast and easy technique. All you need is a MALDI TOF mass spectrometer, like the MALDI-8020 or MALDI-8030, a polymer sample, 1 to 2 mg/ml. For water-soluble polymers, a solvent mixture of 50% acetonitrile and 50% H2O. For non-polar polymers, organic solvents such as THF, DCM, or other solvents the polymer is soluble in. A matrix, for example 5 mg/ml CHCA in 50% acetonitrile and 50% H2O. Other useful matrices for polymer analysis include DHB, dithanol, DCTB, and HABA. It is a good policy to use the same solvent for the matrix and the polymer, so they can be mixed before use. Salt solution, for example 1 millimolar sodium chloride. For other salts, such as sodium TFA, silver TFA, and lithium chloride and others may be used for different polymers. A pipette and tips, and a MALDI target. What is a MALDI-8020 or MALDI-8030? The MALDI-8020 and the MALDI-8030 are fast and affordable MALDI benchtop instruments with positive ion mode, MALDI-8020, or dual polarity mode, MALDI-8030. They feature class-leading resolution of 5000 at MZ2465 and allow you to see well-defined mass spectra. The real joy of the MALDI-8030 is the speed. With sample loading taking less than 90 seconds, you can have your results in minutes. With our fast solid-state laser and our new longer life ion detector, this instrument will reliably deliver robust performance for the long term. How can MALDI be used in our polymer lab? We can use MALDI to help with quality control, reaction optimization, N-group analysis, and polymer degradation studies. Quality control. MALDI allows for fast and easy analysis of polymer compounds and has better mass accuracy than SEC-LC. Synthesis and QC. Looking at the purity of the monomer and the polymer. We can use MALDI for the confirmation of successful synthesis. Is the average mass of the distribution, the Mn and Mz, what we expect? What is the polydispersity? Analysis of negatively charged polymers. Using negative ion mode on the MALDI-8030, we can analyze polymers that cannot be detected in positive ion mode. Polymethacrylic acid is used in tissue culture as a polymer conjugate and in chemotherapy as a nanoparticle drug delivery system. MALDI can be used for QC analysis of this polymer. When combined with Polymerix software, we are able to quickly confirm the monomer unit, the indices, and N-group assignments with a high level of confidence. Polymer degradation. MALDI can quickly help us understand the fate of our polymers as they degrade. Using MALDI, we can generate data to support stability studies, to answer questions such as, how does the polymer degrade? How long does it take for the polymer to degrade? How many times can the polymer be reprocessed before it has undergone significant degradation? Analysis of thermal degradation of polymers. Degradation can produce anomalous components that exert a significant effect on the properties of a polymer. Using a dissolution reprecipitation method, low-intensity distributions were observed. These components increased in intensity as the number of heating cycles increased. Peak data analysis in the EM-STAT solution was able to differentiate the 4 different samples into 4 clearly grouped components. Reaction optimization. Do we need to perform the reaction for X hours, or does it finish sooner? Have we exhausted the precursor? End group analysis. What is the degree of conjugation? Did we successfully attach our end groups? What proportion of our polymer is unreacted? MALDI allows us to confirm the identity and fidelity of the end groups. Moving on to the main topic of this webinar, we will look at the analysis of pegylated vitamin E. Pegylated vitamin E is a water-soluble derivative of natural vitamin E, used to enhance the absorption and bioavailability of poorly soluble lipophilic compounds. The pegylation of vitamin E has been proven to enhance drug solubility, permeability, and stability. Vitamin E succinate is tethered to a polyethylene glycol, PEG 1000. In the following slides, we're going to look at sample preparation and analysis of this important molecule. Sample preparation can be simple. Dissolve the analyte, PEG or pegylated vitamin E, at a concentration of 2 mg per ml in a suitable solvent, 1:1 acetonitrile water. Prepare the matrix, 5 mg per ml CHCA in 1:1 acetonitrile water. Prepare the catenization reagent, 1 millimolar sodium chloride in acetonitrile water. Precoat the sample with half microliter of catenization reagent. Remove the precoat after around 5 seconds. Spot half microliter of the analyte followed by half microliter of matrix. Allow to dry before analysis. Once the sample is dried, it is loaded into the MALDI-8030. It takes approximately 90 seconds for the operating vacuum to be achieved. Once the vacuum has been achieved, we can begin the analysis. In MALDI TOF analysis, we calibrate the instrument using a known standard before then acquiring the sample. In the case of polymers, PEG or polystyrene standards are commonly used. First, we move to the calibration spot. Acquiring the data can be as simple as hitting fire. We see how easy it is to acquire a spectrum for polyethylene glycol. Zooming in, we can see the isotopic resolution of the NMR. We move into the calibration tab and calibrate the instrument. When we hit the calibration button, we see the button turn green, giving us a confirmation that the calibration is good. Now we can move on to sample analysis. Next, we look at pegylated vitamin E. We can see in the polymer spectrum 3 clear distributions in the sample. We will characterize all 3 distributions in Polymerix and explain why we see these 3 distributions. We look at the lower mass area of the spectrum. We see vitamin E at MZ430 and vitamin E succinate at MZ557. We export the data to Polymerix so we can start the analysis. We will use Polymerix software from Sierra Analytics to analyze the polymer data acquired on the MALDI-8030. There are 3 aspects we are looking for when we perform polymer analysis. We are looking to confirm the monomer mass units, as this confirms what type of polymer this is. We are looking for the mass of the distribution. We are looking for the polydispersity, how wide is the range of the mass distribution. We are looking to confirm the end groups. We import the peak list that we exported from MALDI solutions as a chromatogram. Once loaded, we drag between 2 of the most intense peaks, right mouse click and drag. and Polymerix proposes the NMR unit. If this corresponds with what we expect, we confirm this and move on to the next window. The software will propose N groups and adducts based on the mass difference. As this is a custom polymer, we cancel this window and enter the N groups and adducts manually. We enter N groups we expect to see based on our knowledge of the polymer, its N groups, and the solvent used in the sample prep. Polymerix will then model the assignments and assign the peaks to the NMR and the N groups proposed. We start by looking at the main distribution. We enter the alpha N group as OH, a common N group when working in an aqueous solution with a hydrophilic polymer. For the omega N group, we enter C33H53O4, as this corresponds to the formula of the succinated vitamin E. Then we enter the adduct as sodium from our cationization agent, sodium chloride. We enable this polymer series and we see the distribution is moved to the current series tab. Next, we continue to assign the series until the polymer distributions have all been assigned. We assign the N groups for the distribution on the left. Again, we cancel the proposed N groups window and we enter the N groups. OH for the alpha N group, the H for the omega N group, and sodium for the adduct. This is PEG with no vitamin E. H and OH are the N groups for this sample as it is in an aqueous solution. Finally, we enter the N groups for the third distribution. The alpha N group is C33H53O5, vitamin E plus O from the alpha end of the PEG. The omega N group is C33H53O4. Again with sodium as the adduct. When we are finished with the assignments, we see the excess mass for the assigned polymer series is very small. This gives us high confidence the proposed polymer model from the software is a good fit with the observed experimental data. The next step is to send the assignments to the homopolymer analysis tab to examine the distributions in polymer statistics. In the homopolymer analysis tab, we can see the polymer details like the molecular weight, the polydispersity, and the percentage of each distribution present. We are able to flick through the tabs to review the polymer assignments, the residual and assigned masses, and the distribution details. This work has illustrated a clear workflow for the analysis of a PEG with a modified N group. Using the MALDI-8030, we have followed the workflow through from the sample spotting through to data acquisition and analysis. We were able to confirm the series present in the spectra with a high degree of confidence using Polymerix. This characterization allows us to measure the MW, MZ, and polydispersity and the percentage of each compound in our sample. This information can be used to provide evidence for quality control, reaction optimization, confirming N group fidelity, and polymer degradation studies. These aspects are critical for the pharmacology of the drug conjugate. Thank you for your attention. I hope you found this webinar informative. If you'd like to know more about the techniques in this webinar, please get in touch with your local Shimadzu representative or scan the QR code below. Thank you for watching.
Excellence in science. Shimadzu.